Sklearninspection. Description: sklearninspection refers to the process of examining and understanding the behavior and performance of a trained machine learning model built using scikit-learn sklearn library in Python. This involves analyzing various aspects of the model, such as its internal structure, feature importance, prediction accuracy, and potential biases. Inputs: trained sklearn model. The trained machine learning model, which is an object containing the learned parameters and decision boundaries based on the training. Data: feature data. The dataset containing the features used for training and testing the model. It can be a pandas data frame or a numpy array. Target data: the labels or target values corresponding to the feature data. Outputs: model performance metrics, evaluation metrics like accuracy, precision, recall, F1 score, AUC, etc. to assess the model's predictive capabilities on the test data. Feature importance: information on the relative importance of different input features in influencing the model's predictions. Model parameters: the values of parameters used during model training, which can be adjusted for fine-tuning. Visualization plots: graphical representations of the model's behavior and performance, such as confusion matrices, ROC curves, feature importance plots, and decision boundaries. Model explanation: insights into how the model makes predictions, often through techniques like partial dependence plots, SHAP values, or line explanations. Steps: model evaluation: evaluating the trained model's performance on a separate test dataset using relevant metrics. Feature importance analysis: identifying which features contribute the most to the model's predictions. Model visualization: creating plots to understand the model's behavior, feature interactions, and decision boundaries. Parameter inspection: examining the values of parameters used during training to understand their impact on the model's performance. Model explanation: generating insights into the model's decision-making process to enhance interpretability and trust. Metrics: accuracy: proportion of correct predictions made by the model. Precision: ratio of correctly predicted positive cases to all predicted positive cases. Recall: proportion of correctly predicted positive cases to all actual positive cases. F1 score: harmonic mean of precision and recall. AUC: area under the curve, area under the receiver operating characteristic, ROC curve, measuring the model's ability to discriminate between classes. Mean squared error: MSE measures the average squared difference between predicted and actual values for regression tasks. Visualization plots: confusion matrix: a matrix that summarizes the performance of a classification model by showing the counts of true positive, true negative, false positive, and false negative predictions. ROC curve: a graphical plot that shows the relationship between the true positive rate and false positive rate for different classification thresholds. Feature importance plot: a bar chart or heat map that displays the relative importance of each feature in contributing to the model's predictions. Partial dependence plot (PDP): a plot that shows the marginal effect of a feature on the model's predictions, keeping other features constant. Decision boundary plot: a visualization of the decision surface that separates different classes in a classification model. Fine-tune parameters: regularization parameters used to prevent overfitting, such as L1 lasso and L2 ridge regularization. Learning rate controls the step size during model optimization. Number of estimators for ensemble models: the number of individual models combined in an ensemble. Maximum depth for tree-based models: the maximum depth of individual decision trees in the ensemble. Uncertainty methods: Confidence intervals measures of the uncertainty around the model's predictions, typically calculated using bootstrapping or other resampling techniques. Prediction intervals ranges of values within which the model's predictions are expected to fall with a certain probability. Bayesian inference, a framework that provides a probabilistic interpretation of the models. Parameters and predictions. Challenges and fixes. Challenge 1: overfitting. The model performs well on the training data but poorly on unseen data. Sample use case that resulted in challenge 1: a model trained on a limited dataset with complex features might learn patterns specific to the training data, leading to overfitting. Fixes to challenge 1. Use regularization techniques L1, L2 to penalize complex models. Increase the size of the training data. Use cross-validation to assess model performance on different subsets of the data. Employ early stopping to prevent overtraining. Challenge 2: underfitting. The model fails to learn the underlying patterns in the data, leading to poor performance on both training and testing data. Sample use case that resulted in challenge 2: a model with a simple architecture might be unable to capture complex relationships in the data. Fixes to challenge 2. Increase the complexity of the model by adding more layers or features. Optimize model hyperparameters, such as learning rate and regularization parameters. Try different model architectures to find one that is more suitable for the data. Consider using feature engineering to create new features that are more informative. Challenge 3: high variance. The model's predictions are sensitive to small changes in the training data, leading to inconsistent performance. Sample use case that resulted in challenge 3: a model with a large number of features or a complex structure might be prone to high variance. Fixes to challenge 3. Use regularization techniques to reduce the model's complexity. Increase the size of the training data to improve generalization. Employ ensemble methods, such as bagging or boosting, to combine multiple models and reduce variance. Challenge 4: high bias. The model is too simple and fails to capture the true relationships in the data, leading to consistent but inaccurate predictions. Sample use case that resulted in challenge 4: a linear model might not be able to capture nonlinear relationships in the data. Fixes to challenge 4. Use more complex model architectures, such as nonlinear models, e.g., decision trees, neural networks. Add more features to the model. Use feature engineering to create more informative features. Challenge 5: data imbalance. The dataset contains an unequal distribution of classes, which can bias the model towards the majority class. Sample use case that resulted in challenge 5: a classification model trained on a dataset with many more examples of one class than another might favor that class during prediction. Fixes to challenge 5. Use oversampling techniques to increase the number of samples from the minority class. Use undersampling techniques to reduce the number of samples from the majority class. Employ cost-sensitive learning, where the model assigns higher penalties to misclassifications of minority class instances. Challenge 6: missing data. The dataset contains missing values, which can affect the model's training and performance. Sample use case that resulted in challenge 6: a model might not be able to handle missing values properly, leading to inaccurate predictions. Fixes to challenge 6. Impute missing values using techniques like mean imputation, median imputation, or more sophisticated methods like KNN imputation. Use models that can handle missing data, such as decision trees or some neural network architectures. Design features that are robust to missing values. Challenge 7: data leakage. Information from the test data is unintentionally used during training. leading to overly optimistic performance evaluations. Sample use case that resulted in challenge 7 using features derived from the target variable during training can lead to data leakage. Fixes to challenge 7. Carefully examine the features used for training and ensure that they do not include information from the test data. Use proper data splitting techniques to prevent leakage during cross-validation or model evaluation. Employ techniques like holdout validation or time series cross-validation to avoid leakage in time-dependent data. Challenge 8. Interpretability. The model's predictions are difficult to understand and explain, making it challenging to trust or deploy. Sample use case that resulted in challenge 8. Black box models, like deep neural networks, can be complex and difficult to interpret. Fixes to challenge 8. Use techniques like partial dependence plots, SHAP values, or LIME explanations to generate insights into the model's predictions. Choose more interpretable model architectures, such as decision trees or linear models. Implement techniques to simplify or visualize the model's decision boundaries.